Hi, this is Kenny Lee, and let's talk a little bit about impulse. So impulse is part of momentum, where impulse is actually the change in momentum. It's not what momentum is and how much it changes. So if something had a momentum of 10, and then you apply the impulse, and now it has a momentum of 12, well, the impulse was only 2. So it's not how much the momentum is, it's how much it changed. Another definition of impulse is the force applied to an object times how long that force acted on that object. So where work was force times distance, impulse is force times time. So we've got a couple equations for that. So this one I use for change in momentum, and we need a symbol for impulse. I always use delta P, but I've seen some books use a capital J for impulse. But if you distribute this out, that would be the momentum after, and that would be the momentum before. So just simply how much it changed. For the other definition, we can use this, where impulse is force times time. And again, an impulse is a vector type quantity, so direction does matter. In the units for impulse, well, traditionally we use kilogram meters per second, but you can also use Newton seconds. You see in this, we have kilograms times meters per second, and here we have newtons times seconds. So either one of these will work. Some cases you may see one more than the other, but both of them mean the same thing. Now, as one little caveat, since both these equations equal the same thing, we can combine these two to get this. Ft equals mvf minus vo. And that's a good catch-all equation for if one of these doesn't work. We're not going to talk about this one in this video yet, but we've got another video that will probably cover that equation just by itself. So let's do some examples of these. What is the impulse of a 7 kilogram cart that is going from 3 meters per second to 7 meters per second? So I want to know the impulse that makes that change. Well, I've got a mass of 7 kilograms. I've got an original velocity, because that's where it started off at 3 meters per second. And I've got a final velocity of 7 meters per second. I always like making that list. That way I know what I'm looking for. So I'm looking for impulse and what information I have to find it. So since I've got mass and velocities, I want to use this one. Delta P equals m vf minus vo. And go ahead and plug things in. Mass is 7. Final velocity is 7. Original is 3. Do the parentheses first. And we get an impulse of 28 kilogram meter per second. There we go, kilogram meter per second. That's really all it is. These problems are fairly easy. It's just knowing what to look for. And with this unit, the equations kind of match certain scenarios. So it's easier to match them up rather than having one generic equation that solves many different things. Okay, let's try one that looks a little bit more complicated, at least on the surface. There's more words here, and so we'll have to see. So a half kilogram toy train is going 2.5 meters per second. A child gives it a push, given an impulse of 12 kilogram meters per second. And I want to know what the new velocity is if that impulse was in the same direction as the train's original motion. So let's have we're having to go this way. So again, I've got a mass of half a kilogram. I've got an original velocity of 2.5 meters per second. In this case, I've got an impulse of 12 kilogram meters per second. And I'm looking for the final velocity. Well, again, looking at what information I have, this is the best equation to use. And so my impulse is 12, mass is 0.5, final velocity is actually what I'm looking for, and the original velocity is 2.5. So I want to get rid of this half first. So I want to divide both sides by half. So we get 24 equals VF minus 2.5. And then I want to add 2.5 to both sides. So we get 26.5 meters per second. It'll be the new final velocity of that toy train after it suffers that impulse. This time we have a force acting on a cart for a time. And I'm looking for, oh, this one says change in momentum. So am I looking for mass times velocity? Well, not really. That change in momentum, that really means I'm looking for impulse. That's another way that we can designate that we're looking for impulse without saying impulse. So I can have a force of 230 newtons, and it acts over 7 seconds. And again, I'm looking for the impulse, which is change in momentum. With those numbers, this version of impulse will work best. So times a time of 7 seconds. So that's 1,610 Newton seconds, or you can say 1,610 kilogram meter per second. Both those are pretty acceptable answers. Sometimes it's easier to keep it in the original units though. A car has an impulse of 600 kilogram meters per second or 600 Newton seconds. Either way, it's the same thing going into the same problem. Is applied to it. If the impulse is applied for 9 seconds, what was the force acting on the car? So we've got an impulse of 600. Again, you can call it Newton seconds or kilogram meters per second. A time of 9 seconds. And we're looking for the force applied to the object. So with the numbers I'm given, this is the equation I want. 600 equals F, and we've got a time of 9 seconds. So we're just going to do a little division. 600 divided by 9 gives me 66.7 newtons of force applied over those 9 seconds will create that impulse. Okay. Thanks for watching. Tune in again for more physics videos. Goodbye.